Hello, we are back to the Renewable Energy Technology course, the lectures on wind turbines and wind power. I'm Miro, and we will continue with lecture number 2, focusing on mechanical engineering and components of wind turbines. We will talk about blades in this section, and of course the blades and the wind rotor definitely is the most important and the most critical part of any kind of wind turbine. First of all, the fact that a wind turbine can be constructed at all is very much dependent on having or not having the blades for it. And the ability to build the blades with a proper dimension, or that is the proper length, actually defines whether or not the rest of the turbine can be made. Actually, the rest is very easy. Even if not just available off-the-shelf components, everything is definitely tailor-made. Having the blade means that the rest is just mechanical and electrical engineering. Building long blades has always been the governing or the limiting factor for wind turbine development. And this is one of the, well, not that good pictures you can find out there. I tried to modify it a bit and fix the proper numbering. Nicely shows the turbine development, and it's not important at all, but it's nice really to see how the sizes were growing. And again, the primary size we talk about is the rotor size. That would be the diameter of the rotor or the length, the radius, in terms of the length of one blade. In the very early days of commercial power, there were small rotors involved. The power output less or maximum of 50 kilowatt. Now we are far beyond this point. It was a comparatively slow development. However, the actual development, if we compare it in this timeline, is pretty much the same as the development of common electronics. Very explosive, both in terms of size and numbers of wind turbines deployed out there in the field. Approximately at year 1990, the commercial turbine used for installations in the real world was just 40 meters big in diameter and approximately 300 to 500 kilowatt power output. In the middle of the 90s, the machines around 750 kilowatt, 800 kilowatt, and towards the end of the 90s, the 1 megawatt, 1.5 megawatt machines were introduced, typically having a 60-meter rotor. That would be the 30-31 meter blade. Approximately 31-32 meters blade for the 1.5 megawatt rated power output. Towards the 2000s, we entered the race towards creating or developing, building, manufacturing the longer and longer blades. There was a kind of a doldrum here, even if the line of development is cheating a bit. Actually, it was not quite of a rush developing the longer blades because people are still buying actually the machines that are slightly smaller. They are the ones that are being purchased and installed. But the attempts to reach the 3 megawatt output, which demanded approximately 100 meters rotor, that would be the 50-meter blade length, was easily won by several manufacturers, and the step towards 120, 130 meter diameter, the 60-something meter blade that we have right now, it's the state of art right now, was becoming more and more difficult. Now the state-of-art blade is 60-something meters length, the radius of the rotor, and it is enough for 5 to 7 megawatt machines. The rush towards the 160 meter diameter rotor, that would be the 80 to 100 maybe meter blade, we aren't yet there. Whether year 2020 or later or earlier, it doesn't matter. Those blades are only on the drawing board now. How the blade is manufactured. It's a long story. It deserves a full-scale lecture of itself. We will simply now focus on the most important points. the blade remains the most vital, the most critical, the most vulnerable component of the wind turbine. The blade development is actually driving the development of the rest of the machine. The blade needs to be sturdy, not stiff, but flexible enough, not subjected to fatigue or cracks appearing with time, and most of all, cheap enough, but also lightweight. Many different materials can be used. None of them is perfect enough, and the early blades, comparatively small ones, were mostly made of wood or laminated wood or some kind of a steel structures, which is definitely not good because steel is always susceptible to fatigue loads or fatigue destruction. And if you want the simplest possible, you can just have plastic blades. Modern blades are made of fiberglass. And this is not a development purely for the wind turbine industry. Actually, the fiberglass structures come from many other applications. And they were transferred, they were adapted to the wind turbine industry. When this happened in the 80s already, actually it was a very important step forward towards, maybe the deciding step forward towards commercial wind power. How the fiberglass blade is built? Well, pretty much the same as with any other material. You would need inside the supporting structure, usually called the spar. There are several spars inside which actually carry the load. They may be built of different materials, but very often they are exactly of the same material as the profile or the outer casing, the outer surface of the blade. And that material is glass fabric. Different types of glass fabric can be used. And the way to build up the blade is to lay down layers of glass fabric, glue them together with epoxy resin or polyester material. This is the way. In this way you can nicely mold the entire blade, shape it out in the end, finish it, and it's actually the super flexible, super lightweight, comparatively cheap option for manufacturing the blade. It is good enough that at the moment there is nothing better. For more expensive options, probably this would be the only choice towards going to the 100-meter blade. Carbon fiber reinforced resin can be used instead of glass fiber fabric. The root of the blade is the most critical point, the junction point between the glass fibers and the flange. This is, of course, the root section is carrying the heavy loads. Everything that the blade should sustain is transferred through the root to the structure of the machine. And how the root or the flange is made depends definitely a lot on how long life the blade would have. Still, the flange in real action out there has proven to be not the most vulnerable point. If a blade is damaged, it is usually damaged somewhere else, but not in its root section. The root section needs to be strong, mechanically strong, and the aerodynamics of that section are not so important. Actually, the tip of the blade is much more productive in terms of aerodynamics, while the root is mostly dimensioned in terms of mechanical strength. How to produce the fiberglass blades? It's actually a high-tech industry. However, it is loaded up with manual, low-tech skilled labor. This is how, just a wild example, how the different layers of glass fiber fabric are being laid. Glued together, there is a glue spread along this mold, a sheath of glass fabric, then glue again, the next sheet of glass fabric, then the spar, the strut structures holding the load, and the other half of the blade on top. The finish, very dirty business. You will need to have somehow a stash of ready blades, because very often actually the blades are being damaged and you need to replace a blade for a turbine that is already out in the field. The cost of the blades is a governing factor again for the cost of the entire project. Blades, the most difficult components and the more or less the costliest ones, especially considering the fact that you have 3 blades in one typical machine. You have 1 generator, 1 gearbox, 1 tower, and 3 blades. Fractures and failures can occur, and they do occur. Close monitoring and cleaning if the blades get dirty, and sometimes replacement needs to be done. So if you have the machine working and just 1 blade is damaged for any reason, you better replace it. It costs a lot, but you better replace it because you've already invested in the rest of the machine. And there is a long lifetime still left in it as soon as you replace the blade. Is there the limit for the blade length? Are we really going there towards the 100-meter blade? That's a very nice question. We are not going to answer it now, but that's a food for thought. You're welcome to think about it. This is one example here. The blade for the 1.5 megawatt turbine. Many of those are actually working out there, some of them more than 10 years old now, is approximately 31 meters long, the glass fiber blade, the state-of-the-art blade. It is heavy, approximately 4 to 5 tons, 1 blade only. The modern blade for the 6-7 megawatt machine, somewhat above 60 meters long for the 125-130 meters rotor in diameter, is approximately 23 tons heavy. What does this mean? Simple math. 2 times longer, 5 times heavier. If we go to 100 meters length, where are we with the masses? Actually, we are far enough so that the fiberglass material cannot support the blade. The root is not strong enough to support the rest of the blade. Maybe carbon fibers, maybe novel materials need to be used. The blades need to be tested, not only in the design phase, where the whole structure is being primarily dimensioned, but each and every unit of blade being produced is usually tested in lab conditions before it is deployed out in the field. Static load, fixing the blade, stretching it as much as possible, defining the braking forces, and also testing it, each and every one blade being produced. If there is any internal defects or cracks or something, it will break in the testing phase, so you actually skip installing it and then needing to replace it. Fatigue strength, oscillating loads. This is one example here of blades fixed and then flapping constantly for million cycles. And this is what happens in reality. A blade out in the field is flapping all the time while moving across the swept area. And over the lifetime of a typical wind turbine, those flapping motions accumulate to millions of times. It is a bit difficult really to represent exactly the same loading in lab conditions. You would need to wait maybe for 10 years until you flap the blade for a million times, but it's very necessary to do. And some decisions can be made only after a month or something of fatigue load testing. This is just one example, my own picture of how you can test a blade. And you see this is a very, very, very simple old 10 meter only long or less. It's a 5 meter blade for the 10 meter rotor. It's actually pretty stiff. Very flexible and elastic, but it can carry lots of load. This is thanks to the material of glass fiber fabric. Steady loads, nice representation of what happens out there in the field when the blade is in action. Some blades might be a bit more elastic, deflecting quite a lot when they are loaded, when the machine is in full operation and all the forces are acting on the blade. And you remember there is an enormous thrust force just bending the blade. It is dangerous for certain machines because if the blades are too elastic and if for some reason the machine is loaded too much, the blade may touch the tower and destroy itself completely. At that moment, the rotor is completely out of balance. The other blades may also be destroyed. And if you are unlucky, the whole machine will be destroyed. Several millions of investment go down the drain for nothing. This is one example of the torque forces. Now this machine is standing still, but even though it is a nice way to imagine that the blades can also be deflected or bended in the direction of motion, of travel. So this is along the section of the profile. It's not really visible how they are bended, because this blade now is pitched for the machine to be stopped. But of course, those vibrations need to be designed somehow or envisaged already in the design phase, and definitely tested if possible. The major problem for wind turbines are the unsteady loads. This is relevant for all kinds of turbines, but especially a wind machine sitting out there using the wind as a primary energy source suffers constantly from unsteady loads. This is just a wild picture of what may happen with the wind field. It is never ever in history and anywhere super stable and super smooth. First of all, the wind is blowing in gusts, always. You can define those gusts in different time limits or time intervals. But the bottom line is that there would always be somehow a stochastic behavior, if not purely turbulent, at least variations of the wind speed that reaches the turbine, and most of all, variations of the flow field. So the blade here experiences a very different wind speed than the blade down there at that same moment. And regardless of how high or how big our wind turbine is, it definitely is sitting in the boundary layer of air motion above the ground or above the surface of the earth. This difference between the top, when one of the blades is pointing upwards while another blade or the other two are pointing downwards, the difference in wind speeds between those two extremes is sometimes enormous, up to several meters per second. This is definitely an unsteady force constantly at every revolution that the turbine should sustain. First of all, the blades should sustain these forces. They transfer them directly through the mechanical structure to the hub, to the tower, to the foundation, and so on, and to the electrical power output. Especially detrimental and very well pronounced these vibrations are in two-bladed machines. And we can look very shortly at why is that. The unsteady loads in two-bladed rotors can be vital for the mechanical integrity of the machine because of two major reasons. Unfortunately, we don't have time enough for that, but just imagine the two reasons. First of all, the fact that one blade is facing up at the best possible wind speeds for that turbine, while the other blade is exactly at that point directly facing down at the worst possible wind speeds for that turbine. There are only two blades straight against each other, produces a very effective push on the rotor in this way. The top blade performs better. The blade down there, first of all, typical wind profile or flow field is worse. Second, the tower exerts a shadow, so the blade down there can move in this direction. If you are not allowing the whole rotor to deflect somehow or to dampen the load in any way, all these constant jerking motion will need to be sustained through the tower, foundation, and so on, and can destroy your machine literally. There is also another aspect, a bit difficult to imagine, but if you start to yaw the azimuth drive, remember, a two-bladed machine, it is easier to yaw the machine when the blades are horizontal. Actually more difficult, sorry. While it's easier to yaw it when the blades are facing up and down. This rotation. And it is simply explained with, common mechanical theory. Now this, if you start yawing, also exerts stochastic forces or somehow a variation, a jerking force on the whole rotor. The way to deal with this is to have dampening arrangements, mechanical dampening in the hub. This is what renders two-bladed machines, first of all, very, very difficult mechanically, not as cheap as they are supposed to be by saving one blade, and actually in terms of lifetime, not to mention that they are perceived as ugly and very intruding to the eye, they actually do not live long because of those vibrations. This is the primary reason for selecting the three-bladed machine as a state of art. Quick review of possible damages. Cracking, breaking may appear at any time due to various reasons, mostly fluctuating loads. Touching the tower in action destroys the blade. The blades can be struck by lightning. If a lightning hits the machine, it will definitely hit the blade facing upwards. And if the blade doesn't explode, literally, it may simply be damaged. Sometimes dirt and ice can accumulate on the blade. It's easy to imagine what happens with ice. Actually, on the leading edge, you start building up a whole range of ice particles which totally alter the aerodynamic profile of the blade. Consecutively, the forces on the blade are also changed, altered, and the vibrations suddenly may become in totally different mode. So one of the blades vibrates in one mode, the other blades in another, and the whole turbine is ruined. It may not be ruined immediately, but definitely the lifetime of the machine will be decreased if you allow it to operate too long with iced blades or ice-loaded blades. Sometimes for various reasons you can see such pictures, and this is like a private photo from England. It can look really funny if, well, one blade damaged, the other blade totally missing, and okay, what shall we do with this machine? Sometimes the decision is scrap it. If you have to replace all three blades and bring all the machinery there and so on, sometimes the best choice would be simply to sacrifice the entire machine. Quick summary. Blades remain the most expensive, the most crucial, and the component that is governing completely the development of bigger and bigger machines. If we have the blade, we can easily build the rest. Modern commercial blades are exclusively made of glass fiber. The more expensive ones of carbon fiber fabrics, glued together by different types of polyester or epoxy resin materials. There is actually one big topic, nobody mentions it yet, but it might soon become a very important, very relevant problem. What shall we do with the old blades? Glass fiber is not really easy to recycle, and if we just dispose them of, where would that be? Blades are vulnerable and can often be damaged by various reasons. You have to monitor your turbine. You cannot just leave it for 10 years out there without any maintenance, without monitoring, and so on. Close monitoring of blades is very important. If a blade is about to be damaged, you have to detect this as soon as possible. Repair if possible, replace if necessary, but do not leave it to destroy the entire machine. This is the end of this section. Thank you.